All right, in this video, I'm going to cover section 2.1, the bisection method. So chapter 2, we're going to talk about, we're going to learn the root finding problems. Numerical method for solving root finding problems. So what's the root finding problems? So root finding problems is simply saying that we solve the equation of the form c that f of x equals 0. So yeah, right here, f of x equals 0. So first, we get the 0 on the right-hand side, and then we consider left-hand side as definition of function f of x. So now, the one of the basic bisection method is the one of the basic method. So we'll see. We're gonna study. So to apply the bisection method, the function f of x must satisfy the assumptions of intermediate value theorems. So what that means? So what's the intermediate value theorems? The intermediate value theorems are saying that if function is continuous on closed interval AB, and then the f of A is not necessarily equal to f of B, then there exists the certain x value for given um, the L, which is L is between f of A and f of B, and then such that f of x equals L. So what that means, intermediate value theorems means this: for any choice of the function value between f of A and f of B, there exists x value between A and B. So it makes sense because the function f is continuous. That's a big assumption, right? So and then we tweak the intermediate value. We tweak the assumptions. I mean, adding one more the assumptions. F of A times f of B is less than 0. What that means? F of A times f of B is less than 0. It means that the sign of f of A and the f of B are different. So f of A is positive and f of B is negative. F of A is negative and f of B is positive. So then there exists what the x such that f of x equals 0. It means that there exists what x-intercept. In other words, in algebra, there exists what solution of the equation f of x equals 0. So if you the need if you want to figure out intermediate theorems more clearly, just look at the chapter 1. Okay, so now I'm going to explain what Bisection method briefly. So think about this one. Example 1 in the textbook. So we want to solve this root-finding problems. Function f of is given, a cubic polynomial, right, equals 0, has a root on the closed interval 1, comma 2. So now then, what are you going to do? The oh, give me a second. So now then, first one, we're gonna find the middle point between a1. Let's say we're gonna set a1 equals 1, b1 equals 2, and then you're gonna find the middle point between a1 and b1, which is that's gonna be what 2 uh, a1 plus b1 divided by 2, is it right? b1 over 2, is it? Now then, and then we're gonna figure out the sign of f of p1. Okay, so then, so if sine of p1 in this example, sine of p1 is what? Sine of f of p1. Okay, f of p. We evaluate a function f at x equals p1. So we see that f of p1 must be positive, and then we're gonna the update b1 to p1. So let's say this is b2. Okay, and then we're gonna set a2 is just a1. Okay, so why? Because now the then we can still apply the intermediate theorems. So A1 sine of f of A1 is, see that, negative. Sine of f of P1 is what? Positive. Then by the intermediate value theorems, there exists that intermediate value theorem guarantee that there exists what, root between A1 and P1. So now we set A1 as A2, we set P1 as B2. Okay, B2 right here. And then we're gonna find out the middle point between A2 and B2. Let's say this is P2, okay, right here. P2 is the middle point between A2 and B2. Now then, we're gonna figure out sine of f of P2. So evaluate f at P2, which is right here, and the sine of f of P2 is one negative, right? And then what? If we just set P2 as a B3, then we're gonna get big problems. So let's say A2 is A3 and the P2 is B3, then what? We cannot apply intermediate value theorem because the f of A1 is negative and the f of f of A3 is negative and the f of B3 is also negative. So that what? That doesn't satisfy what the assumptions of the in IVT, right? Intermediate value theorem. So then what, we're gonna set P2 as A3, right? And then we're gonna use B2 as B3. Okay. So now then we can see that the universe is just narrowing down, right? You see that? So here's starting from A1 right here, and then B1, and then A2, and then B2, and A3, and B3. So is the universe is getting, is narrowing down, and then still what? I mean, all the universe contain what? The root, right? So in keep doing repeating this process, eventually what, we're gonna get the approximation. I mean, the sequence of A1 and sequence of A and the sequence of B is gonna approach the root, right? So it means that the P, let's say this is P1, this is P1, right? P1 and P2 and P3. So that middle point will approach to what? The root P. Okay. So that's the algorithm of bisection method. So now, let's see. All right. So now then here one more assumptions. The root in closed interval a comma b is unique. Okay. So keep in mind this. And then now, so let's see algorithm in detail. So starting from the this one, setting a1 equals a and b1 equals b, and then p1 is what? The middle point between a and b, or we can say a1 and b1. So a1 plus b1 divided by 2, or we can the express the middle point is like this, but either one's just fine. Now we're gonna evaluate function f at p1 to figure out sine of f of p1, right? Then we can we're gonna get two cases. Case one, f of p1 equals 0. But this is really good, right? F of p1 equals 0. It means that p1 must be a root, right? The root. So we stop. Then with the your okay, we just stop. And then case two, what if f of p1 is not equal to 0? Then we can think about two cases, right? So now f of a1 times f of p1 is greater than 0. It means that, I mean, assuming that f of a1 is less than 0, then f of p1 must be positive, right? The other case, f of a1 times f of p1 is less than 0. Okay, so then it means that what? F of a1 is assuming the f of a1 is negative, then f of p1 is uh, yeah, I'm sorry. So I think I made them confused. F of p1, assuming the f in this case, f of a1 is less than 0, then f of p1 is less than 0. So it means that the sign of f of a1 and f of p1 are the same. Okay, negative, negative, or positive, positive. In this case, negative, positive, or positive, negative. We can think about two cases, right? So now in here, f of p1 is less than 0. We gotta update a1, b1, p1. Okay. So first of all, we have to figure out which, I mean, in this case, f of a1 times f of p1 is greater than 0. It means that both sign of f of a1 and f of p1 is positive or negative. In this case, what we gonna update what a we're gonna set a2 as p1 and then p2 equals p1. So you see that here, it means that here is mm, yeah, right here. Let's say this is here is a1. Okay, a1 is nothing but a. Okay, b1 is nothing but b. Okay, so here is a p1 right here, right? Then in this case, f of a1 times f of p1 is greater than 0. In this case, then we set what the give me a second, a2 is p1. This is gonna be a2. Okay, and the b2 is nothing but just b1, b2. So the left what in a closed interval a1 and b1, left endpoint will be updated to p1. Okay, this kind of is. So and then we're gonna find the p2, which is right here. Okay, so starting from p1 right here, and the p2. Okay, so now let's say the true, I mean exact the what the root is right here. Let's say is a root is right here, p. Okay, this is a p2. Okay, right here. Now then what? And then we're gonna find out the definitely maybe p3 is maybe right here. Okay, and then p4 is maybe right here, depending on problems. Okay, so now you see that the interval is getting narrows. Okay, so now let's see. What if let me see, fa1 times f of p1 is less than 0, so it's positive negative or negative positives. I mean, so okay. Then we set a2 equals a1, b2 equals b2 equals p1. Okay. So I mean, you may wonder that how come? So keep in mind this. Why we you may just wonder that why in this case we set a2 is p1. Eh, why in this case we set p2 is p1. Otherwise, what? Otherwise, the assumptions of intermediate value theorems. This one. I mean, the additional assumptions. This one will not be satisfied. Otherwise, that's why we have to what update a b p so that this assumption will kept satisfied. Okay, keep in mind this. So yeah, okay. Now next one, let me see. Okay, so now you see, I mean, so right here, give me a second. Okay, so we'll see. Yeah, evaluate. Now next one, and then we evaluate f of p2. So and then f of p2 evaluate, and then so FOP evaluate FOP2, and then we can think about two cases. FP2 equals 0, it means that P2 is a root. Yeah, stop. Okay. In the other case, FP2 is less than 0, then update A to B2 P2. So now that we see what. Okay, so can you see that? I mean, what case? What cases? We have to think about this. FOP2, FOP2 times F of what? Oh, A2, right? Is greater than 0 or less than 0, right? Greater than 0 means that what? The sign of f of p2 and f of a2 is just same, right? Then the A3 gonna be what? P2. Okay. And then what if f of P2 times f of A2 is less than 0? Then sign of f of A2 and f of P2 is different. Then what? P2, I mean, what? P3 gonna be P2. Okay. Let's keep like this. So now, so we repeat this process while I is less than or equals to n0 and not. And not is the number of iterations. Okay, in your program, in your code, the bisection method in your code, you have to design your code to set the number of iterations. Okay, manually. So at each, or you can just design your code automatically stop when the pi closer enough. I mean, pi is just approach to the root within the error point, for example, within the error 10 to the negative 6. Okay, and then just code just return the number of iterations used with the error, and then yeah, the approximate at the root. Okay, so that depends on depends on you. Okay, so this is up to you. I mean, so now at each step, the length of interval known to contain a zero of f is reduced by a factor of 2. That makes sense because the interval is reduced by half, right? So it's advantageous to choose the initial interval as small as possible. Yeah, so um, if you just give me a second. So initial value is also initial interval is also important. Okay, so then but you can just figure out, but not because you don't have to figure out the best initial interval, but the applying the just find out the initial interval such that f of a must times f of b must be less than 0. Keep in mind this. Okay, so for example, in this example one, f of 1, because the function is given, right? So f of 1 and f of 2, it can be figured out, right? So f of 1 times f of 2 less than 0. Then what about f of 0.5 times f of 2? If less than 0, yeah, then 0.5 comma 2 is the better initial interval than 1 comma 2. Okay, so in this case, let's see. And then the other one is this. Keep in mind this. A1, A2, A3. The AI must be less than P and the BI must be greater than P, so that every steps the intervals must contain the root. Keep in mind this. Now, how can you figure out that every how can you figure out whether or not just interval contains a P? You just figure out the sign of f of ai times f of bi. So f of a times f of bi is just less than 0. Yep. Then the interval must contain the p. Okay. So now here we're gonna use relative error. So relative, what's a relative error and absolute error? So please read my lecture, the chapter 1, or just read the textbook in chapter 1. Okay. So relative absolute error, the formula should be in the chapter 1. Okay, my lecture note. Now, and then, so in this example, p minus p13 absolute value divided by p. So simply saying the relative error is a true solution minus approximate solution divided by true solution and take absolute value. Okay, so that's the relative errors. So, and then the calculating finding the p13, okay, based on the algorithm of the bisection method. Okay, this is less than b14 minus a14 over absolute value of a14, and then this is less than or equals to 9.10 to 95. So 95, that is called the what the give me a second. Yeah. So mm, give me a second. So here, this is the significant digit is the largest non-negative integer in the exponent in that scientific notations. So normally the error is expressed as the integer times 10 to the negative some non-negative integers. So normally that integer must be one integer. Okay. So one digit integer. Okay. So here, so that's going to be then in this case five. The significant digit must be at 5. Okay, it's not 4. I think this is typo. So now then, why? So this is that the we're just continuing to solve the example 1. Okay, so now p minus p13 is less than or equals b14 minus a14. Um, so the computing p13 and b14 and a14, you then yeah, is the you're gonna get this b14 minus a14. BA14 is 0.000122070, and then so here definitely what A14 must be absolute value must be less than P. How come? Uh, so see, let's say this is the A, okay? This is nothing but A1, right? This is B. This is B1 right here. Then we just finding a sequence P1, P2, P3, then the interval was getting narrowed down, right? So let's say here's A14, okay? And then here's B14, okay? Where is P? P must be what? P must be, what? Must be in the interval, right? Every single interval. So P is right here, okay? So now then you see the absolute value of A14 must be what? Less than absolute value of P. Now it makes sense, right? Okay, so now this doesn't make sense, right? Okay, so now then, actually A14 is absolute A14 is a numerator, a denominator of the right hand side of fraction, a right hand side of inequality, and then absolute P is a what? Denominator of left hand side. So since absolute A14 is less than absolute P, and then we see that this is a numerator of the right hand side of inequality, and then this is a numerator of left hand side left hand side of inequality. So that fraction has a bigger numerator and then less denominator. That means that fraction must be greater than this fraction. Okay, does it make sense? So definitely you have to write your own code based on the algorithm, okay, of the bisection method. Okay. So, and then try to find out P13 and the A14, B14, and then check, you know, that this number and then this number too. Okay. So that's your job. Okay. So now let's move on. Then let's say theorem 2.1. So once we design the algorithm, okay, and then it works, but that's not done yet. Okay. So we have to figure out how fast, how accurately that method can find the approximation, can approximate the true solution. I mean, true root. Okay, so we need to figure out this. Then we have to apply we have to use mathematical theories. Okay, first one, theorem 2.1. Suppose that f is continuous. It makes sense because to use in intermediate value theorems, function must be continuous on the closed interval. And then f of a times f of b is less than 0. Okay, so we need this, right? Then Bisection method generate a sequence Pn approximating 0 peeps. That's nothing but root, okay, of f. So keep in mind this. Our goal is to solve the what? Root finding problems. F of x equals 0, okay? So then Pn minus p, that's the absolute value of, absolute error, actually, absolute value of the difference between the approximate solution to a true solution. That's called the absolute value error. This is less than what, this is bounded by b minus a over 2 to the nth power. So what is this? This is what? So you see that here, this is upper bound of absolute value errors. How come? So from that inequality, we can expect that how many iteration do we need to get an approximate solution within the error. So b minus a over 2 to the nth power. Then for example, so let's say a and b are given. Let's say a is 1 and the b is 2 in the example 1. So numerator must be 1, right? So 1 over 2 to the nth power. So I want to get the approximate solution had just within the error, for example, 0.2 0.25. Then n must be 2, right? Because 1 to the 2 to the 2 square, this is 1/4, which is 0.25, right? Okay. So now, then how many iterations do we need? Just 2. Okay. So the n equals 2. Iteration 2 guaranteed that what our the approximate solution obtained by the bisection method with n equals 2, 2 iterations. Then this is then this theorems, that inequality error bound is called error bound. Error bound guarantee that the accuracy is like this, 0.25. Okay. So now then, it's proof. Okay. So listen carefully here. All right. So for each n is greater than or equals 1, and the bn minus an is equal to the 1 over 2 to the n minus 1 times b minus a. How come? Yeah. So let's just prove this first. Okay. So right here, bn minus an is equal to 1 over 2 to the n minus 1 times b minus a. So first one, b1 minus a1 is b minus a. That makes sense, right? And then b2 minus a2 must be 1/2 and b minus a. Uh, why? Because what? See, okay, see, this is a1. Can you see the a1 right here? And this is a b1. Okay, all right. Either a1 is either a1 becomes a2 or b1 becomes b2. Anyway, so a2 new inner becomes a like this here, a2 b2 or a2 b2. Either a1 becomes a2, b1 becomes b2. The inner will be narrowed down by half of the a1 and b1. So that is what the distance between a1 and a2 and b2. This is a2, b2. Okay. In the case of the a1 becomes a2, and then b2 p1 becomes b2, or p1 becomes b2, and then p1 becomes a2. But either case, look at the new universe, a2 b2, either this one or this. That's the half of the a1 b1, right? So that makes sense, right? Doesn't make sense. And then now, then what? Next step, a3 comma b3 gonna be what? Half of the inverse of a2 b2. So this is 1 over 2 square. So in doing this, b minus a1 is going to be what? 1 over 2 to the n minus 1 times b minus a. That makes sense, right? So then So now then we're gonna calculate this absolute value errors. P minus absolute value of P minus P is less than or equals P minus A n. Why? I told you. Since what? P is greater than A n. K minus A n is always less than P. Okay? Okay, K minus this. So now then since P is greater than A n, so P n minus bigger number must be less than Pm minus less number than P. Makes sense, right? And then what? Pn is what? Pn gonna be, middle point, what? Middle point of An and Bn. So Pn can be expressed as 1/2 times An plus Bn minus An. This is gonna be this 1/2 times Bn minus An. And then what? We just figured out that Pn minus An is equal to what? B minus 1 over 2 to the n minus 1 times B minus A times 1/2 is this. Okay. So now, actually, b minus a times 1 over 2 to the nth power, that's a geometric series, right? In calculus too. So b minus is a constant term, so, and then 1 over 2 to the nth power is this geometric series, right? So the sequence Pn converts to P with the rate of convergence 1 over 2 to the nth power. This is called the big O. It's called big O. Okay. So what's a big O? Big O represent the rate of, give me a second. So this one represent the rate. So certain that one is, so the constants times 1 over 2 to the nth power. Okay. So normally this big O represent the rate, and then big O, for example, H, that means certain constant times H. Okay. So normally, yeah. So here, in this case, what is C? B minus A, right? B minus doesn't, it's just can be considered as constant, right? Because B minus A will not be affected by what n. Okay, it's the number of iterations. So yeah, it can be considered as the constant. So C times over here. So 1 over 2 to the nth power. So now the Pn is equal to P plus BO 1 over 2 to the nth power. Okay. So n is increased. Then what? BO will decrease by rate of what? 1 over 2, by rate of 1/2, right? So now then, let me see. So now example 2. So we want to find out the approximate root of the root defining problems f of x equals 0 with accuracy 10 to the negative 3. Now then, what? We need to figure out the optimal number of iterations. Okay. So then we use the theorem 2.1. The theorem 2.1 says that absolute value of error is less than or equals in this. That must be less than or equals 10 to the negative 3. And then we apply A11, B11. So this is given in problems. Okay. So that one is given. Okay. So we plug in, 1 and 2 into A and B. And then we got this 2 to the negative n is less than 10 to the 3, negative 3, solving that inequality. Then we can figure out optimal number of iterations. It turns out that n must be. So we got solving that inequality, we're going to get 9.96. But let's see, number of iteration must be integer. So we can round up. Okay. So now here, error analysis gives only a bound for the number of iterations. And in many cases, this bound is much larger than actual number of recurrence. So theoretically, the optimal number of iterations is 10, but numerically could be different. Okay, it could be different. So you may get the that errors maybe not 10th iterations, but maybe 7th iteration or even 6th iterations. Okay, so this one is the what? Yeah. So sorry, can maybe you cannot say the optimal, but rather than saying optimal, but the sufficient. Okay, so the sufficient number of um, the iterations. Okay, so this one, that number guaranteed that you could, the bisection methods will return the approximate root with that accuracy at least. Okay, so that's the bisection method. Okay, so let me stop here, and then next time I'll cover section 2.2.